Okay, so in this part of the video, we are going to go now into 12.8, an ideal gas. This video will be probably one of the longest one because I'm going to go from here, guys, to 12.9, the ideal gas law. And I'm going to solve, guys, as many problems as I can to apply now this ideal gas law to various situations here, because it has many applications here in regards to ideal gases. Now, what is ideal gas? And I'm going to read, guys, the definition from your textbook. I think it's a really good one. And so ideal gas is a gas that would obey gas laws exactly over all temperatures and all pressures. Now, the way to look at the ideal gas is that the ideal gas does not really have the intermolecular interactions. So in other words, when these molecules come close to each other, they really do not stick to each other. They just pass by each other. When they collide, they transfer all of the kinetic energy from one atom or molecule into the other. Now, does it really happen? The ideal gas is ideal gas. Certain gases do behave like ideal gases, and the list of these gases, guys, in this 12.8, so you just can go in and just read about the identity of these gases. Now, what I also, guys, want to mention here is that if you want the gas to behave more like ideal gas, and if there are intermolecular forces that prevent that from behaving as ideal gas, what you want to do, you want to minimize this intermolecular forces. And one of the ways you can do it is by decreasing the pressure and increasing the temperature. So when you do the decrease in pressure and increase in temperature, what you guys are actually doing, you are moving the molecules further away from each other by decreasing the pressure. And when increasing the temperature, the molecules do not spend considerable time close to each other. They just zoom, they just go by one another with such a speed, such as velocity, that they don't even have time to interact. So, and that's one of the ways, guys, you can make the gas ideal, even if there are some intermolecular forces between the gases. Now, so what is the ideal gas law now? So the ideal gas law now is I'm going to read it from the textbook. The definitions here are really good. Is the gas law that describes the relationship among the four variables: pressure, volume, molar amount, and temperature for a gaseous substance in a given set of conditions. Now, all they did here is that they combined four different gas laws, such as Boyle's law, Charles's law, Gay-Lussac's law, and Avogadro's law, to just form one equation. And if you guys remember, the P times V was the Boyle's law, the Charles law was V over T, the Gay-Lussac law was P over T, and the Avogadro's law was V over N. So when you combine all of these together, you get the PV and RT, where the R is just the combination of all of these constants, they all combined together, and the R, guys, is just 0.08206 atmospheres times liter over mole Kelvin. This is the ideal gas constant. Sometimes they call it, if you go to the physics books, they call it a universal gas constant. And so the way they find this universal gas constant, I'm checking your textbook, it's not really the way you're supposed to find it. You usually study the gas over certain temperature range and certain volume, also certain pressure. And then so what you do, you construct a graph, and then you pretty much get the R from the graph. Again, if you guys want to, go to, more deeper or learn how to get the R, I can supply you guys with some literature. Generally, you find this derivation or, using the graph and the extrapolation of the R in physical chemistry. Okay, so here we're not concerned on how we get the R that much. Again, it's we validate it from the experiments. And so the usual problem here, you're going to be given, you have 1, 2, 3, 4 different terms. This one is always the same. This is the ideal gas constant. So when you're given 4 different terms, guys, one will be missing, will be unknown, so you will have to find it using algebra. Okay, so let me take a look first at example 12.11. Example 12.11, and I want to see, guys, what's given here. And let me just erase, everything here that occupies some space, so that I can now solve this problem here. So I can state now my what's given, what's desired, etc. All right, so let's read the problem. The colorless, odorless, tasteless, toxic gas, carbon monoxide, is a byproduct of incomplete combustion of any material that contains the element carbon. Calculate the volume in liters occupied. So this is the first piece of information given. Number of moles is 1.52 moles of this gas. Also, I'm giving guys the pressure here, 0.992 atmospheres. And the temperature here, guys, you got to be always cautious, guys, with the temperature here. So they're giving you Celsius right away, convert it into the Kelvin, guys. Okay. So again, they don't use to 73.15, so I'm not going to use it here either. So when you add now 65 to 273, you pretty much got 5 plus 3 is 8. Now 6 plus 7 would be 13. Just remember 1. So it's 338 Kelvin. Okay. So all you have to do now is they're asking you guys to find, let me just calculate the volume in liters. Okay, so let's do it. So one unknown here is the volume. I'm going to restate now the formula. And again, you guys, you're allowed to use this formula in the exam. If you forget this formula, it's not important to remember these things. So the volume is equal to now nRT over P. All I have to do now, plug in the numbers and solve the problem. So I got 1.52 moles times the R, which is 0.08206 atmospheres liter mole Kelvin here, times my temperature here is 338 Kelvin, and I will divide it by the pressure, which is 0.992 atmospheres. So it's important, guys, to set up everything right, to display all the units here. Moles and moles cancels out. Atmosphere cancel out. Kelvin cancels out. And now I'm wind up, guys, with the liters. And that's exactly what the volume supposed to be, guys, in the volume. Supposed to be in the units being expressed units of liters now. So let me do the calculations here. So I'm going to now plug 1.52 multiplied by 0.08206 multiplied by 338 Kelvin, and I'm going to divide that by 0.992. So here everywhere, guys, I got 3 significant figures here. So my final answer now has to be 42.5 liters. And that's the way, guys, you solve now these problems, okay? Now, I'm going to go now solve as many problems as I can here in the examples. I will explain you guys step by step each example. So now the next example is 12.12 on page 514 of the textbook. All right, let's read what's written here. So nitrous oxide, N2O, is naturally present in trace amounts in the atmosphere. Its source is a decomposition reaction occurring in soil. What would be the temperature? So now I know I have to find the temperature here. In the degrees Celsius. So this is what's given, guys. The given here is the mass of a substance, 67.4 grams. And I'm going to state, guys, what kind of substance, because I will have to get the moles in here, obviously, right, to use the ideal gas law equation. And also to give me, guys, the pressure here, which is 5.00 atmospheres. And they're also stating, guys, the volume here, 7.00 liters, okay? So the question is, they want me, guys, the temperature, and the temperature has to be Celsius here. They want me, guys, to find the temperature in Celsius. Okay, so that's not a problem. I'm going to state now the formula again. And I will need this, so temperature will be equal to now P times V over NR. And so now all I have to do is plug in the numbers. So my now pressure is 5.00 atmospheres times V will be 7.00 liters. I will divide it by number of moles. You guys got to be careful here now. This is the mass of N2O. I will actually convert on the fly, guys, into the moles. I'm going to say 1 mole of N2O, and I have to do now the calculations of the molar mass. And I know that nitrogen is 14.01. 14.01, I'm going to multiply that by 2, and I'm going to add now 16.00. So I have now my molar mass here is 44.002 I don't know why I put 1 in here. 0.2 grams of N2O. So canceled. And so in the bottom also, don't forget, guys, I got the R 0.08206 atmospheres, liter, mole, Kelvin. So let me do now my unit canceling here, because remember, if I want to find the temperature, has to be Kelvin here, and then in the moment I will, guys, convert that into Celsius. All right, so I got the atmospheres, and atmospheres here are canceled. I got the moles here, and I got the moles here canceled. I got now the liters here canceled. The only unit that is left appropriately will be my Kelvin. It will go up here. So let me, guys, do the calculations now. So this is the way I will perform the calculations. So again, I need to get to my calculator. So I will say now 5 times 7, of course, is 35. I don't have to plug it into the formula, but since I'm going to do now more calculations, more step in this calculation, I will divide it now by 67.4, and then I will multiply that by 44.02, and I will divide that by 0.08206. And so my final answer here is, I got 3 sig figs everywhere, so it's going to be 270, looks like 9 Kelvin here. And so in order to find now my degree Celsius here, temperature degree Celsius, I will convert that 279. Let me just correct this. Hold on now. 279 Kelvin. And I mean, you can just do straight minus 273 to get the Celsius, but I really want to do it the right way. Kelvin cancel out. I mean, not cancel out. This minus this, you're going to get a number. I'm going to put in parentheses here and then multiply 1 Kelvin is equal to 1 degree Celsius. That will be the conversion, guys, in here. And so when you do 279 minus 273, you got 6. You got 6 degree Kelvin. Kelvin cancel out, and then multiply by 1 degree Celsius. The final answer is 6 degrees Celsius. And that's how you guys can now use this ideal gas, law equation to pretty much solve, this problem now, finding the temperature. Now, the next problem, guys, that I'm going to do here in this video, before I go into the next part of the chapter, I will now do now the part 12.10, the modified. This video will be a little long, but I think since these concepts all connected, I want to keep them together, guys. So I'm going to do now 12.10, the modified forms of the ideal gas law equation. Now, I'm going to go straight, guys, and solve the problem here. And I will show you guys my logic here, how I solve it. And then as I solve it, you guys will understand the concept. So I'm going to do example right away. Example here, I'm going to do 12.13. And so this is what I'm given here. I'm given a 3.30 grams of the chlorine gas of CO2 gas. And occupies, so I'm also giving, guys, the volume here, 1.20 liters. And I'm also, guys, giving the pressure. So be real careful, guys, when you use the ideal gas law with the units of pressure, because remember the constant itself, the R has the atmospheres. So you will have to convert always, guys, the millimeters or whatever the units you got for pressure into the atmospheres to match the units, guys, of pressure in the ideal gas constant, the R. So now the next one will be the temperature, given 33 degrees Celsius. And based on data, calculate the molar mass of the chlorine gas. Okay, again, guys, I'm going to do all of these conversions in a moment. But what's interesting here is they want me, guys, to find out the molar mass of this gas. So my rationale here, I can derive the formulas here that they do here in the textbook real quick. So here's the way they derive it. They use the PV, nRT, and then they also say that the molar mass of a substance is the ratio of mass over number of moles of the gas. Now these two formulas have something in common, which is the N. I'm going to say now the N in terms of the mass and molar mass will be M over the M here. And so the next thing I'll do is I'm going to take this and substitute into this ideal gas law equation. It will be PV is equal to M over this M times RT. And so now we need this. So the molar mass will, I just gotta cross multiply everything. It will be now MRT over, and I'm gonna bring the PV here in the bottom. So this is pretty much the formula, guys, that you see in the textbook here, and that's how they got it. I like to do it a little different way. I like to do it a little logical. I'm still gonna use, guys, these two formulas. I'm gonna say molar mass is the ratio of mass of the substance over its number of moles, and then I'm gonna state the PV and RT. So I already know that I have given the mass of the gas, so already halfway there solving this problem. The only thing I need is just to solve for the number of moles, and the number of moles I can get from the ideal gas law here. So that will be N is equal to PV divided by RT. So I'm gonna find out now what the number of moles are. Once I got this, I'm gonna plug into this formula, and I don't have to use this whole thing here. And remember it, because I know some of the students, for some reason, do not want to derive this formula. And what they do is they like the way I solve now in 2 steps this problem. So again, guys, it's up to you. I can do both ways. I will still get the same answer. So the number of moles here is equal to now the pressure here, guys, just remember, has to be atmospheric pressure, because the R in this case here, the R has the units of atmospheres. Just be, guys, real careful. So I'm gonna say 1 atmosphere contains 760 millimeters of mercury here. So I just converted, guys, this pressure into the atmospheric pressure times the volume. It must be liters, of course. It is liters as given, 1.20 liters. And then I'm going to divide this by now 0.08206, the constant atmosphere times liter mole Kelvin. And then I'm going to times the temperature. Remember, guys, this is the 33 Celsius. 1 degree Celsius equal to 1 Kelvin. Oops, canceled. And so what I need to do now is just add 273, adjust for that 0 discrepancy, 273 Kelvin. And so my temperature here will be now plus 30 will be 3, and now 306 Kelvin. Now, let me start canceling the units, and if I mess something up in here, I would definitely know it, because I wouldn't be able to, guys, to get the moles as my only unit that will be staying after I cancel all the other units. Okay, let's do it. Atmosphere cancels, liter will cancel, Kelvin will cancel, and the mole, of course, will come up here. And so I got the right units here. Okay, so all I have to do now is to now use my calculator to come up now with the final answer. So let me do so. All right, so this one I'm gonna do now, 741. I'm gonna divide now by 760. I got now my atmospheres times 1.20, now divided by 0.08206. And I'm also, guys, gonna divide it by 306. And so what I got here is I got number of moles here, and I'm gonna report 1 extra digit, guys, beyond the significance, because that will be my intermediate result here, 046. I got a 5 in here, 3 significant figures, but then I'm gonna also report a 9 in here. Okay, so my last step is to find the molar mass of the gas. I'm gonna use the mass. I'm gonna use now this formula here, 3.30 grams divided by number of moles here, 659 moles. And as you see, guys, the gram over the mole will be nothing else by the molar mass. Okay, so let me do the calculations. 3.3 divided by 0.04659, and I got 3 significant figures. So I got now the 70.8 gram per mole, guys, the molar mass of the chlorine gas. And if you compare now to the textbook answer, I'm not even sure. I think they just use the whole formula, plug everything in. I did it, guys, a little different way. But if you like my way, please do it. If you don't, to use their way. They're just using this formula, which I derived for you guys before. Now, so this is the correct answer. So what are the problems you may, guys, now be facing? They may ask you guys to find out the density of the gas. And it's pretty simple here to find the density of the gas, because again, you use the molar mass formula and also the ideal gas formula. And so when you, again, gonna say that the number of moles is equal to the ratio of mass over the molar mass, You now substitute this in instead of this number of moles. You're gonna have a PV M over M RT. As you can see, guys, remember the density is equal to M over V. So you got the M, you got the V. So you're gonna bring the M and the V to one side, and then everything else to the other side, divided by RT. And now you can substitute this by D, and you can say that P times the molar mass over RT, and that will be now, guys, the way to calculate the density of a gas. Now, let me now do the, I'm gonna solve now this example. I'm gonna do this example, guys, 12.14. I'm gonna solve now the problem, applying now this formula that I just derived. And so the gas, in the gas law calculation, air is often considered to be a single gas with a molar mass of, let's say I'm giving guys here molar mass of 29 gram per mole. And on this basis, calculate the density of the air in grams per liter on the hot summer. And also the guy is giving you 41 degrees Celsius. Right away, convert that into the Kelvin without even hesitation. Okay, so we're converting it on the fly here. And when the atmospheric pressure, so also give you guys the, let me just make a little space here for my pressure here. Okay, so the pressure here, the stating is, they're already giving me, guys, this one in atmospheres, which is awesome. I don't have to do any conversions. And again, so all you have to do now, you got this M, you're gonna plug it in here. You guys got the pressure, you're gonna plug it in this here, instead of this term. You guys know the R is always constant, the same number. And then when you do this, the temperature, you're gonna plug it in here, and that's how you're gonna find the density. So let me, guys, now start plugging everything in. And so this will be my pressure, which is 0.91 atmosphere for the pressure. I'm gonna now times the molar mass, which is a 29 gram per mole. And then I'm going to now divide that by 0.08206 atmospheres, liters, mole, Kelvin, times the temperature now, the 41 degrees Celsius plus 273, 273 plus 41, so that will be 4, and now that would be 11.3, so it's 314 Kelvin here. And all you have to do now, guys, you know, just use a calculator and figure out the answer. So let's do it. So my final answer must be two significant figures because of this 0.91 is only two significant figures. So I'm going to do 0.91 times now, and also 29, only two significant figures, times 29 divided by 0.08206, and then divided by 314. So my final answer, guys, the density of this gas, again, I only have two significant figures, so that would be 1.0 gram per liter. So let me show you guys how I got these units. Mole cancel out, Kelvin cancel out. So what I got here, gram left over liter, and that would be, guys, my final answer. So this is the way, guys, to do these problems. Also, there's example 12.15. This one, guys, you can actually do it on your own, calculating molar mass of gas given its density. All you have to do now, you can either use, guys, the two formulas that I already combined before and gave you guys the relationship between density, of course, and they are derived, right? The D is equal to P times molar mass divided by RT. So if you need to, guys, now you can also figure out the molar mass based on the density of the gas. You're going to say that the molar mass here is equal to the density times the R times the T, bring this one up, and divided by the pressure. So all you have to do now, once you do this example 12.15, you know the density of the gas, you know the R, it's always the same, you know the temperature, they'll give it to you in the problem, and you know, guys, the pressure in this particular case. So they want you guys now to calculate the molar mass. And so all you have to do is just plug in and get the answer. So if you still, guys, have difficulty with example 12.15, please let me know during the live lectures. I will solve this problem with my pleasure, and will help you guys to understand the concepts. So I'll see you guys in the next video to wrap up the chapter number 12.